Welcome you all in this Cryo-EM course. Last class I was discussing about the work function, how it is different between the thermionic emission, Schottky emission and field emission. So there is a change in the work function that is helping us to take out the electron from the electron gun. Now let me show you how to go for a electron gun and how to design an electron gun. In electron gun, first we will focus on that how we can make a simple thermionic emission gun, and then later stage we will discuss about the field emission gun and Schottky emission gun. So here so for any electron gun we need a very sharp tip. From that electron is going to come. For the tungsten filament, most of the time you can see a very hairpin type of sharp so this kind of sharp tip is available in case of tungsten filament. So we'll show the tungsten filament, how this tungsten filament look like. Now this is called Wynot cylinder. What is the spelling of Wynot cylinder? H-N-E-L-T. This is called the Wynot cylinder. Now this part, it will be connected. Definitely we need some kind of connectivity between those, otherwise electric current cannot go. So this will be, and here there is a connection, this one, it will be connected through our one resistant, it will be connected here, and then finally entire thing I can connect through this, that so there will be some kind of voltage difference between this, that is some kind of electric field we have to give it, that what kilovolt. If you want a 50 kilovolt, you will get a 50 kilovolt. Now at the end there will be an anode also which is connected, which is near this diagram, which is help us to pull out the electron. That is the anode we are talking about, that always there should be a anode which will pull out the electron towards the down. So this anode, it will be connected, so this will be a negatively charged, this will be a positively charged connection, and this anode, this is called the filament. This is called filament, this is called anode. There is a resistance will be there, so we don't have to know this entire circuit. What is required, we should know this is the overall architecture. If someone is asking us what do you have in the gun, that's the three major component. One will be our cathode, one will be our cathode or filament. Then we have our Wynot cylinder here that I mentioned. This both are the Wynot cylinder. This is the one and other one is connected. This both, if I just connect this will be one part of the inert cylinder and this is the other part of the inert cylinder. I'll erase this one, it will help me to draw rest of the part, and then this is our anode which is helping us. If the electron will come out from the filament, this will pull down the electron through the column. Now let me erase those part, this will okay. So now here if you just consider that okay, I have a filament and we are considering this is a 300 kV microscope, or you just consider that okay, there is a negatively charged electron that is 300 kilovolt. Now this is called bias, or our inert cylinder will keep a magnetic field or electric field in such a way that it will be higher negative charge than this particular value. Why? So here I am just trying to give you an example. If you just consider we have a very long hair and I am driving a bike and I don't have any cap or helmet and I am driving that bike. If I do that at a very high speed, my hair will be all over my face and it will be looking very ugly. So first what I need some kind of cap to put my head. So if you just consider that these are the electron, so all these hairs are the electrons and it can, because of the air, it can spread all over. So even if you are using a thermionic emission, using this electric field, you are hitting that filament. So thermionic emission, it is something like that in like the bulb. So when we have the bulb, we have a electric current and the resistance is so high, it will generate a heat and then it will illuminate the light. Here it is also the same thing, we are hitting that filament with a 2500 Kelvin to 3500 Kelvin heat. Using this electric current, when you are hitting, it is generating, it is overcome the work function and it is generating some free electrons. Now that free electron can go any direction. So if we just consider some electron can go this direction, some electron can go this direction and some can go. So here we need some kind of protection or some kind of cap, so electron cannot spread all over. So electron can come only towards the down, and that is the another reason we have this cap, and immediately after that we have an anode which can pull this electron towards the column. If this is true and then we are keeping a magnetic field somewhere here, so what will happen? We will get an electric field something like that, and gradually you can see so this is the field, that magnetic field, it is there. And I will just remove this particular line. So we are using a magnetic field or electric field which has some kind of electric field, and that will be much more negative than what this value is. So if we just make this one minus 350 kilovolt, then it is much more negative. Whatever electron it will come, even that electron wants to go in this direction, there will be a repulsive force, and there will be a force to this electron to come and follow this pathway only. So if we just use that red line, what is happening? All these electrons are coming out from this, so they cannot travel in any other direction because there will be a repulsive force, and it can go only one direction. So you can see this electron can go only one direction, that is that it has to come towards the bottom. So whatever electron it will come out, it will go like this, and then there will be a repulsive force. That force will push that to converge in one particular point somewhere here, and when this electron beam, it will come and merge somewhere one particular point where this field of this V naught cylinder, it will be less, and that is called almost equipotential line, where this is the equipotential line where these electrons can come and merge together and form a give a crossover point. So this is the first point where electron is coming from the electron gun and merged together in one particular point, and when they are merged together, this anode, it is connected with the accelerating stack. Also the multiple stacks are connected together, and at the end it is grounded or earthing is connected. So here you can see the electron volt is minus 300 kilovolt, or the energy of that electron is minus 300, and then gradually we are accelerating the electron, because this is a anode. It is not like that it is minus 300 and immediately we are putting it 0. So gradually we are increasing the speed of that electron, and electron can go through this column. And that is the reason, last class when we are talking about that lambda, what is the value of this wavelength of the lambda, we told that we always have to consider that relativistic effect, that 2 EV 1 plus EV by 2 M0 C square, and entire thing will be 1 by root. By root. So this is the reason you can see this is the anode, and it is gradually, because this anode is gradually connected with the accelerating stack, which is increasing the speed of the electron, and it is not from minus 300 to 0 immediately, it is gradually going down. So minus 300, then it may be the minus 270, then minus 240, and going down towards the 0, and then you can see that whatever electron is concentrated in this particular point, they are gradually accelerating through this column, and that is the reason we always have to consider that relativistic effect when we are considering the speed of the electron. Now this is the first crossover point of our electron, and this first crossover point means where all the electrons are converge in one particular point. This is basically regulating our brightness. If we lose our electron somewhere in this region, our brightness is going to affect. So that is the reason this V naught cylinder, which is behaving like a cap and giving a unidirection to the electron, that is also very important, that what should be my V naught cylinder voltage, which is maintaining the electrons, and it will come out from the filament and converge in one particular point. So this crossover point, it is telling D0. Okay, and not only that, this angle is also playing an important role. Let me draw that part somewhere in a very simple form. So we don't need those electric current and those parts, so we'll just erase those at this moment, and we'll just use this one, that simple form, that okay, this is my filament, this is my V naught cylinder, this is the field, and gradually if you just consider that field is going like that, so this is the equipotential area. Now electron is coming out and merging in one particular point here. Now whatever we have to align, if you want to align this microscope, filament, everything, it should align in such a way that everything goes through this line. This is called the optical axis. This is called optical. Okay, so this is the optical axis. Now electron beam converged here, that I mentioned that this crossover point is called D0. Then we have anode and the accelerating stack, which is regulating the speed of the electron. Now this called the gun crossover point. So this is called the gun crossover point. After that gun crossover point, there is no regulator like Winot cylinder or cap kind of thing. Only this anode is there, which is pulling the electron down. So one, there is an optical axis, and then electron will go through this. Okay. So now there is an angle, it is coming, that is called alpha 0I. So this angle, it is called the solid angle. Okay, so here it is depending on this D0, how much current is there, that electron density, that is I, it is denoted by, and this solid angle. So the brightness of the microscope is depending on this particular point, which we can label it like that. Okay, beta is the I by pi D0. D0 is the cross section of this one. We are taking the radius square by pi alpha 0I square. So next, if we just simplify these things, what we can get it here, we can get it here like 4I, this is 4, or let me do it, so many of you will be not familiar with this much mathematics, so better to go. So this pi, it will be pi square, then D0 square by 4 to alpha 0I square. So finally you will get it 4I divided by pi square D0 square 0 square. So it is depending on the solid angle, what is the angle here, and that is basically the solid angle means in two-dimensional we will consider that, okay, this is a normal angle we are talking about. Solid angle something like that, if you want to draw this angle, so something like that. So in 3 dimension, if we just consider this is a 3-dimensional angle, this is called the solid angle. Okay, so we are considering this solid angle of this one, and then the crossover point, the D0, and total current here. So that is denoting our brightness. So now if we lose some electrons somewhere here, that is going to affect our brightness. In this particular sense, we want to talk a little bit more that, okay, we did this diagram, right? So what is going to happen if we just use the same diagram? So first let us draw that optical axis. This is our optical axis, this is our electric field of because of this Winot cylinder, and then electric currents are coming and merging somewhere here. That we already did it, right? Now there are three possibilities are there, so we should discuss little bit about that one. So I'll just remove the optical axis at this moment, and all these rays, there is no point to keep all of these rays at this moment. So the possibilities are this, that okay, I have a Winot cylinder here, definitely Winot cylinder is here, right? Now we are keeping a very less magnetic field or electric field here. So what is going to happen in this particular case? Electron beam will be spreaded lot here. It will spread it because this magnetic field or electric field is strength is very low, and when it will come here it will be very difficult because all these things will be spreaded. Your anode is somewhere here. So you can see the beam, if you just consider that D0 is not a point source anymore. Previously when you are looking at, you can see because of this magnetic field or electric field, this D0 is all the electron beams are coming and converging in one particular point, and this point source electron, it is easy for the anode to pull out towards the down, and that is basically helping us to get all the electrons, and it should go through the condenser lens 1 and condenser lens 2 and fall on the object. So definitely if the beam is spreaded too much, it is going to affect our brightness. This is one possibility. What about the other possibility? Other possibilities is that okay, we have a similar kind of filament. Only change we have, a stronger bias field. So now we are using stronger, you can see it here. What will happen, that I already mentioned couple of times, because if our anode is somewhere here, this is anode, this is our cathode. Okay, so electron beam, it will come out here, there will be a repulsive force, and it will help us to converge somewhere here. So you can see there is a D0 and it is looking like a point source. So most of the electrons from here, it can go through the column, because entire things is not spreaded like this one. So definitely this Winot cylinder electric field called the bias. See, this bias is a very important, that how much we should keep it, and that will help us to extract that electron properly. Then what is the another possibilities? Another possibilities is that we have this, we have this one, then we have a lens filament, and now we are using a very strong electric field. So if we are using a proper electric field, it will really help us, that if we are constantly increasing the field, what will happen, it will block some of the electron and it will try to converge the electron somewhere here. So if we are using more stronger, it will push the crossover point up. But now if we are using a very strong field here, so it is going to block all the electrons and electron cannot come out. So whatever electron it is coming out through this, it will just go back. So no electron can come out. So there are three possibilities are there here: very less electric field or magnetic field, this one, the very less electric and magnetic field, which is making the crossover point is very broad, and that is not helpful. So this is the best scenario. We can use that bias current in a different form, which will helping us to make the proper crossover point and get all the electrons towards the column. And the other part where we are using a very strong magnetic field or electric field, which is blocking all the electron which is coming out from the filament, and it is not usable at all. So in these circumstances, I want to talk little bit more about, so in next step, next diagram, definitely it will be field emission gun. So what is that field emission gun? Let's see, check the field emission gun, that how this field emission gun is made. So if we just remove all of this, so field emission gun is comparatively straightforward than our thermionic emission. So in this field emission gun, what we are using a cathode. So same filament or similar kind of filament we have to use it, there is no doubt about that. So we have, let me use the different color. So if I just use this one, so here we have, okay, fine, we have, this is the line where this will be connected, this will be connected, okay. This for the heat energy, we are using this one, and then this will be, now our filament, our filament will be connected somewhere here. So this will be our filament, okay, and from this is the source where electron will come out, and then this is our cathode. We all know that pointed cathode. So if we just mention this, this will be our pointed cathode. So this is our pointed cathode, and then after that there will be a two anode, that anode 1 and anode 2. So if we just look at here, you will get similarly, there is a two anode, and now this is the part where it will be connected definitely with the electric current source, otherwise we cannot get any electron beam. So if we just consider, this is negatively charged and this will be the positively charged because it is anode. So if we just consider that U equals to 1 to 50 kilovolt and kilovolt, this is positively charged, this is negatively charged. Now here we have the two anode. To anode, this is called anode 1 or first anode and the second anode. Okay, so now what is happening, electron beams are coming out, so definitely you need some heat energy, but here there is a major difference between the previous filament and this particular filament, that there is a back to back two anode systems are connected. So we are using the heat energy to hit the filament. When electron is loosely packed and then there is a very strong positive charge we are applying, chances are very high that electron will come out and pulled by this anode towards the column, and exactly that is happening for the field emission gun. So here we are hitting that filament, but definitely that heat energy is much lesser. So something you can say 100 Kelvin. Okay, so that heat energy is 100 Kelvin, and then back to back these two anode, it is helping us to pull out the electron, and you can see comparatively this heat energy is much lesser than previously when we are using the tungsten filament. In case of tungsten filament, we are using, this is the heat energy, that 2500 to 3000 Kelvin. For Schottky filament, we use some 400 to 1800 Kelvin. But in this case, you can see comparatively heat energy is very less, and we are using two anode system to pull out the electron towards the column, and we are getting a crossover point here, and the electron is going in this direction. So this is the two major difference between the thermionic emission and the field emission gun. Field emission gun is, we don't need that much heat energy, only 1000 Kelvin is good enough. So if we have 1000 Kelvin only, that means your electron beam is much more coherent, you are not giving that much heat to your filament. So filament will be efficiency will be much higher, lifetime of the filament will increase, and we get a coherent electron beam. On the other hand, for the thermionic emission, your beam will be not that coherent and filament lifetimes will be less. So we will stop it here today, and next class we are going to discuss how to make that kind of Schottky filament and field emission gun and thermionic gun, and then we will talk about the electromagnetic lenses also. Thank you very much for your attention.